joining us. So as she pointed out, my name is Josh Brister. I'm in charge of product management here at AE. And we are here this nice fine morning to talk about UL 1741 Supplement A and a little bit about California Rule 21 and mostly what it means for you. So if you love hearing about codes and standards and certifications and regulatory, you are going to love the next hour. I imagine most of you are most interested in kind of what it means for you and how you can be compliant. So we'll talk about that as well. We will have time at the end to answer questions, so feel free at any point to type a question into that field. Love for this to be interactive wherever possible, and want to make sure we get you guys prepared to meet this rollout. So with that said, get started. Here's what we'll be talking through today. What are these requirements? Where did they come from? How does UL differ from IEEE versus Rule 21, et cetera? How does all of that kind of fit together? I think, for me, most interesting is how will this help support the grid? We'll talk through how will it be implemented, what do you need to look for, and of course, how do I stay compliant? So no big surprises, that's what we're aiming for. Alrighty, what is UL 1741 SA? You're going to hear it referred to as SA, as Supplement A. So officially, the standard is UL 1741, standard for inverters, converters, controllers, and interconnection system equipment for use with distributed energy resources. I thought about creating a funny acronym to shorten that up, but it's really long and I couldn't find anything. So that's the official name. In essence, this is the test standard by which inverters are certified for interconnection to the grid with particular respect to grid voltage, grid frequency. So in previous years, 1741 was developed in lockstep with IEEE 1547, which is the official name, standard for interconnecting distributed resources with electric power systems, and 1547.1, which is the conformance test procedures for that standard. So in previous editions, these were generated in lockstep, and 1741 was adopted from IEEE. What we've seen in this iteration is a need, particularly from states like California and Hawaii, to go above and beyond what was called for in the existing IEEE standard. There was a working group put together several years ago, I believe colloquially called the Western Utility Work Group, that was pushing for some of these smart inverter standards, based in large part off of what had been developed from in previous countries. So this work group represented the inverter industry, electric utilities, NREL, EPRI, and at one point it looked like there was just going to be a Western utility standard, which from a manufacturing and distribution standpoint would have been really hard to have kind of two existing or coexisting standards for different parts of the country. So you all made the decision to just kind of roll this into a supplement to the existing standard and be able to roll it out kind of off period. So the timing here, this was approved in September 8th, 2016 for implementation 1 later. That's why we get this weird rollout date of September 8th, 2017 that we'll talk about. SA is short for Supplement A, so it's an addition to the existing standard designed to create a standard for inverters to be more capable of dealing with the volatile and dynamic grid. And then, bring it in a way to create a standard for inverters to actively manage grid functions. So this is, while we're going to have some bumps in compliance and rollout and timing, I'm really glad to see this come to market because I think it's really going to deliver on the promise of distributed energy resources, and this will help to counter some of the arguments you see from certain sides about the intermittency and the unreliability of distributed energy resources. So really happy to see this rolled out. How does UL and Rule 21 and Rule 14H, how do all of these things fit together? So, essentially what you see is there's a national product certification standard, which is UL 1741. So this is a set of standards that every approved product has to be able to meet in some form or fashion. These are kind of, generally speaking, standards that say the product has to be able to do this, and this at a bare minimum. From there, this next layer, local interconnection agencies. So typically these are regulatory agencies like utility commissions, so CPUC, HECO, NYSERDA. They're open to grant more specificity, provided it doesn't conflict with the product certification standard. So for several years, Hawaii Rule 14H went above and beyond UL 1741. We'll see some specific examples of this in a few slides. Finally, this gray layer, and it was not gray intentionally. I realize that's a little tongue-in-cheek, but this gray layer of local interconnection requirements are coming down from the local utility districts. So they can specify local interconnection requirements more precisely, provided it's approved by the regulatory agency. So sometimes this is calling for an additional meter. Sometimes it's additional, disconnecting means, etc. In this case that we're going to be looking at today, it's actually set points, timing.
I'm out.
And of course, not featured here is local AHJs who are going to inspect for safety, have certain call outs on, conduit wire sizing, labeling, etc. But frankly, that's another topic and another webinar. So how will 1741 SA be implemented? In short, what you're looking at on the left are the two state jurisdictions requiring grid support effective September 8th. And the specificity there is that all projects permitted and approved for interconnection on or after September 8th will need to be certified to UL 1741 Supplement A. The jurisdictions that we're aware of at this point, of course, Hawaii, California, but also some local utility districts running pilot programs such as APS in Arizona, Green Mountain Power, and I'm sure there's a couple more out there of the more progressive utility districts that look forward to using this functionality. I think we all see a future where this type of functionality is going to be rolled out nationally. The timing on that is basically going to be when IEEE 1547 catches up. There will be a new UL 1741 standard that rolls Supplement A in. The timing that we're looking at as a market is likely 2019 code cycle. But if local utility districts continue to pick this up and run with it, it could be a lot earlier than that effectively in your area. The disclaimer I like to put at the bottom of any slides when I'm talking about regulatory is always check with your local AHJ and utility district because at the end of the day, they're the ones that are going to give you your interconnection agreement and your PTO. So make sure you're signed off with them. But this webinar should get you prepared for those conversations. And if you know this is being implemented, you'll be able to get the right product to be able to get PTO. Labeling requirements. So in addition to being on the approved state lists, such as the CEC list, the Hawaii approved equipment list, etc., the product will need to be physically labeled as a grid support inverter rather than simply grid interactive. So I've put here a couple call outs, and if you can see my mouse, you'll see the SolarEdge HD Wave inverter. The label on the right side actually lists grid support, utility interactive, non-isolated photovoltaic inverter. Grid support there is, of course, the words that matter. Got a couple examples here from an Outback Radian. Grid support, utility interactive. Those are the words you're looking for. So, we can help all of that, and we've got part numbers set up where there's any question on whether it's going to be grid support or not. We've got the product differentiated. But of course, if you've got product that you've already purchased and want to make sure you're compliant or not, that's what you're going to be looking for on the label. Okay, so what is this new Supplement A actually testing? So there's some existing attributes and functions from 1741 that are continue to be tested, and there's some new ones as well. And I'll walk through some specific examples of these in a few slides, but let's just walk through it right now. Anti-islanding. So this is the function that detects the formation of a standalone grid, aka detects that an island is forming, and disconnects the inverter from the utility grid. This is active. This function is active by default in the certification standard. Voltage ride-through. So this is a function that allows a grid-support inverter to continue outputting power or ride through a temporary over or under voltage scenario. So outside of the very tight voltage specifications that come kind of standard in UL 1741, this allows an inverter to ride through some brief intermittency or voltage fluctuations that a grid might see in normal operations. Frequency ride-through is going to be very similar, so that's going to allow the grid support inverter to ride through a temporary under or over frequency scenario. Ramp rate is actually two different but very related functions. So these are power gradients or slopes that will govern how quickly an inverter accelerates up to full active power after a temporary interruption, such as cloud cover, or shutdown due to a non-qualified grid. So the rate at which an inverter ramps up is the way to think about that. Specified power factor. This one's getting more interesting, I think, as you think about grid support features. So this is a function that allows the inverter to be set to a specified power factor. The standard and most manufacturers are going to ship at 0.95 to unity power factor, but this is of course one of these settings that's open to being predetermined by a local utility district. So by operating at a fixed power factor, systems can help maintain a stable grid voltage. I think maybe a more dynamic way to do this is the next function, which is volt var. So this is an enhanced or dynamic way of using power factor to support grid voltage. Whereas a specified power factor, essentially a constant Q, is just going to peg the inverter to a specified power factor based on that utility district. Volt var would adjust the ratio of reactive power based on what grid voltage the inverter is seeing. So a dynamic way of dealing with power factor fluctuations in a local grid. So those are all mandatory. These are all things that 1741 SA says you have to have in your local source requirements documents from the state. Optional. Now these are kind of optional depending on which state. Frequency watt and volt watt. So frequency watt is going to be the active control of output power as a function of grid frequency, and very similarly, volt watt is going to be controlling active power as a function of grid voltage. So, a good way to think of this is think about anti-islanding, think about the ride-through functions, and then think about frequency watt and volt watt as kind of increasing levels of grid support. So in just an anti-islanding mode, if frequency or voltage falls outside of those kind of harsh stated thresholds, the inverter is going to power down. In ride-through, you're allowing it to temporarily ride through a under or over voltage, under or over frequency. And then when you add the frequency watt and the volt watt, you're telling the inverter, I don't want you to shut down. I want you to keep operating. But, and this is where we're going to add some additional functionality, I may want you to actively curtail your power output. Or in the example of a storage product, I may actually want you to inject power onto the grid above kind of available power. So, these are, concentric circles or, Russian dolls, if you will, of increasing functionality that local utility districts and SRDs can deploy for grid support. So we'll walk through a couple examples in a few slides of what these are going to mean, locally. Great question here. Why is this stuff needed? So the short answer is grids are facing increasing penetration rates on PV, in some cases saturation. And the original 1741 standard had very strict thresholds on anti-islanding. The voltage windows and the frequency windows were very narrow. And essentially this was brought about as a safety concern. If a grid voltage or frequency was fluctuating, there was the concern that linesmen would be working on that grid, and the utmost concern was safety. We didn't really, at the time these standards were developed, we didn't really envision a future where we would have things like grid support inverters who could actively manage to support the grid. So these, for safety's sake, these anti-islanding standards were very strict and very black and white. Unfortunately, that leads to issues of their own. So if you've ever installed a system at the end of a long feeder, you've probably seen systems where the inverter shut down due to a non-qualified grid, usually because of over voltage, but sometimes because of frequency. So at the end of this long feeder, depending on how that transformer is loaded, you're going to see voltage fluctuation. You're going to see voltage, well above or well below nominal. At that point, you've either got to work with the utility district to have that transformer recapped, or they've got to give you special permission to adjust the anti-islanding settings of that inverter. Neither of those is a particularly appealing scenario, but that's the harsh reality of some of our grids, unfortunately. Similarly, we've seen systems in the past in Hawaii which had a kind of normal steady state frequency of 57 hertz. So, you'll see in some of the coming slides, 57 hertz is non-qualified in almost every scenario. So in those instances, the local utility district passed a sign off where, the inverter settings would be adjusted accordingly. So you see that, with increasing PV penetration, with these harsh existing standards, you've got the possibility for some really troubling cases. So I'll throw one out there. Hawaii, nice sunny day, not too hot. Loads are lower, inverters are just kind of pumping out power onto the grid. Loads are stable, but more and more wattage is being supplied from PV. So without intervention by the local utility operator, stable grid, stable loads, increasing generation, there's only two things that can happen. Either more generation is going to be taken offline, which is usually what happens behind the scene. But in the event the utility is not able to get ahead of that, voltage and frequency are going to rise. They're going to rise to the point where the inverters are no longer seeing a qualified grid, and then they're going to start dropping offline as the voltage and frequency come back in spec. Now, we've lost some generation because inverters have gone offline. Now maybe the voltage and the frequency are back in spec and the grid qualifies. 5 minutes later, due to that 300-second countdown, inverters are going to come back online. Voltage and frequency are going to rise again. So you have this, really troubling tripping on, tripping off, tripping on, tripping off that can happen. You've also got issues when cloud cover passes, or I don't know, say a August 21st total solar eclipse. You're having these inverters come offline. 2 minutes later, the clouds or the eclipse passes, and the inverters are going to rush back to full power output. And grid operators have to be prepared for that to happen. The only things that the grid operators can do is use things like combustion cycle turbines and capacitor banks, et cetera, to support the grid. It really impacts their ability to run base load, which is, part of the argument against distributed energy resources in the past. So I think the hope is with these new standards, by showing off what some of these systems can do to support grid functions, we're helping prove our case for DERs in the future. So that hopefully paints the picture of why these standards are needed and how they'll help. What I want to cover now is, as I mentioned earlier, these concentric circles of functionality, how they kind of fit. So you see here a list of all of the separate functions that the Supplement A certifies products to. Anti-islanding, voltage ride-through, frequency ride-through, volt VAR mode, specified power factor, the two ramp rates, normal ramp rate and soft start ramp rate, and I'll walk through those. Frequency watt is optional, volt watt is optional. And then, of course, there's local specific utility functions that aren't necessarily covered in Supplement A. The example here is remote connect and disconnect from the grid operator for those systems. So that is specified into HECO Rule 14H. That's one that's not specifically called out by Supplement A, but it's not necessarily in disagreement with the standard, so it is allowed by the grid operator. So we'll see in a few slides kind of how these utilities are going to adopt this and where their specificity and where their precise requirements are going to come into effect. think the best thing to do at this point is look at some of these features and what they actually do, what they specifically do, and see how they'll be implemented locally. So the first one is low or high frequency ride-through. The green, and what you're seeing here, the y-axis is frequency in nice, full hertz chunks, and the x-axis is time in seconds on a logarithmic scale. So this first kind of orange line, this is 0, this is 10 seconds, or excuse me, yeah, 0.1 second, 1 second, 10 seconds, 100, 1,000. So this first green band here is, essentially what the standard used to be, up to 60.4, down to 58.5. Anything inside that band, kind of nominal state, the inverter continues outputting power as long as voltage is in the proper window and there's array voltage. What's new are the blue and pink boxes. So the blue box, represents a scenario of low frequency. So this may be a temporary solution, maybe not. Here's what's really different. The existing 1741 SA standard said anything in this blue box, the inverter needs to trip and wait until the grid is qualified and then count back up from 300. So in this scenario, with this existing, this is kind of the default standard from UL, the inverter is going to ride through for up to 299 seconds. Now, without implementing frequency, what does ride through mean? It's going to continue outputting available power for 299 seconds. If at that 300th second, it still qualifies the grid as being kind of inside this box, it's going to trip and disconnect. Of course, this real low frequency range, sub 57, let's call it, inverter must trip within 0.16 seconds, which is essentially the one cycle. Similarly, on the high end, there's a ride through. So if the inverter qualifies the grid as being above 60.4, but below or equal to 62, continue to ride through for 299 seconds. And then, of course, very high frequency, above 62, inverter must trip within 0.16 seconds or 1 cycle. So this is the standard default settings from UL 1741 SA. When you work down at the local level, they're going to be able to specify the exact set point. Is it tripped at 57 hertz, or is it 56.5? In theory, it could be a utility district where their grid runs relatively slower or faster. So all of these boxes may move up or down. Similarly, the utility may request a ride through that trips at 200 seconds or 150. The standards provide that leeway, that flexibility for local utility districts to decide what works best to support their grid. So that's frequency ride through. You'll see in a few slides how you can couple frequency ride through with frequency watt to build a much more dynamic grid. Voltage ride through. I did this one second because there's kind of an additional step that you see in voltage ride through, or an additional scenario that you didn't see in frequency ride through. So again, we see a green box which constitutes normal operation, very similar to what we had with the original 1741. And you see here that the y-axis has been unitized. So this is kind of at percent of nominal. So 120 or 240 or 208, et cetera. So in any of the high voltage 1 or high voltage 2, high voltage 1 or low voltage 1, low voltage 2, there's actually 2 operating modes that can be assigned. Mandatory operation, which means you must keep operating, and mandatory cessation, you must stop. The local utility is going to provide set points, durations, where the inverter shall continue operating, cease exporting wattage. What you see here in this, what is different that I'll cover now, and we'll show this up here. So this is the, effectively the pre-existing 1741 standard, which said anything in this green box must keep operating. anything in this that falls in this light blue low voltage window must trip within 2 seconds. In this blue window must trip within 2 seconds. Anything down here in this gray box must trip within 1 cycle, so 0.16. And high voltage must trip HV1 must trip within 1 second, and HV2, this real high voltage, must trip immediately. So you see this existing standard being very kind of binary, on or off, and in many events, very quick tripping. What you see with 17.1SA, more surface area, basically meaning more ride-through capability. And the other thing that's different is 1741 originally had this binary on or tripped state. What we see now with these very low voltage regions is the inverter must cease energizing but not trip. So actively curtail power but do not disconnect. So what the standard is anticipating is that temporary low voltage scenarios will quickly be remedied and the inverters can come back online without the 300-second countdown, which I think personally is a huge improvement. Again, what we saw with frequency ride-through, we see here with voltage ride-through. So we're adding additional functionality. We're adding the inverter to be kind of programmed in a dynamic fashion. And when you couple that with the optional voltage volt watt, you see that you're able to combine these for creating a really dynamic, resilient grid. We'll talk about volt var. So this is the point in the presentation where I get to post my disclaimer that says I am not an electrical engineer. So I'll explain here what I know. Volt var is an interesting operating requirement. So it builds on the premise that an inverter is essentially a programmable power supply. The inverter is going to qualify a grid, and then it's going to mimic that grid, as close as possible given its programming. It's going to follow that grid in terms of frequency. It's going to follow that grid in terms of voltage. And while it's going to increase its voltage 1 or 2 volts to be able to provide a potential power flow out to the grid, it's going to mimic that as closely as possible. What we have the ability to do now through these grid support standards is to alter the power factor that the inverter is presenting to help support the grid. So it's going to use the inverter as sort of a grid stabilizer by either adding inductive or adding capacitive reactive power. So I've got here an image cribbed from SMA, and what you see here on the x-axis is the inverter terminal voltage. What you see here in the y-axis are the different power factor quadrants. So you see here in step 1, the voltage is inside this kind of nominal window, which the utility district is going to tell you what is V2, what is V3, what is considered kind of normal operating voltage. So in this zone, the grid voltage is nominal. The inverter is going to add purely active power as long as it's specified within that specified power factor. So kind of normal operation mode. In example 2, so kind of a higher than nominal voltage, that's going to add inductive reactive power. In zone 3, it's going to add capacitive reactive power. So it's going to do this. It's going to adjust VARs to help keep the grid voltage from oscillating. It's going to act like a shock absorber, and it should help, stabilize grid voltage. That's assuming, of course, that your local utility district hasn't required you to use some, bizarre constant power factor. Volt VAR mode should kind of override those constant power factor settings. So if they've specified a constant power factor of 0.95, but they've done the set points right on volt VAR mode, if you are outside of that voltage window, the power factor will adjust. So interesting stuff, and I'm looking forward to seeing some studies on how this actually helps support some of these, small, less resilient grids. Ramp rate. So this is another really beneficial one in my eyes. What we're talking about here is, of course, how the inverter ramps back up to full operating power after an event, either cloud cover or a disqualification. So what we see here in this graph is an example of a reconnection. So On the y-axis is production, on the x-axis is time. So what we see here is, the inverter is ramping up. Looks like kind of maybe a morning cycle. And then for whatever reason, it drops offline. So either the grid disqualified, or I suppose it's possible that this was based on the timeout. I think this was a disqualification is the scenario they had in mind. The dotted line would be kind of power production under the old standard. So once the inverter counts back up to 300 and the grid's qualified, the relay is going to close. The inverter is going to jump back to full power and continue ramping up. Continue exporting full power based on availability from the array. That can be a really, pardon the pun, but a really rude wake up for a grid to see an inverter, let's assume this is a 5 or a 7 kilowatt system, drop offline, jump back online and requalify and continue working. In a scenario where you've got, 2 or 3% PV penetration, 1 out of 100 homes, 1 out of 200 homes, the grid can absorb that. In a scenario that we're hopefully going to continue seeing where, 20 to 40% penetration, that can be, I won't say can be. That is a lot harder for a grid to stomach without having huge voltage and frequency fluctuations. So now we've programmed in the ability for a utility district to define this ramp rate. So as a percentage of nominal current per second, how quickly is it going to accelerate? And again, there's 2 operating modes covered up here: normal operation and soft start. Normal operation refers to active inverting, how the inverter ramps back up when more array wattage is available. So if it detects cloud cover and it sees that basically sees the wattage and the available wattage increasing, it's going to actively curtail that ramp up, to as defined by this slope given from the utility district. Soft start occurs when an inverter requalifies to grid, which is probably what we're looking at here. So a great functionality that I'm glad was included in this standard. Now we're going to get into one of the optional standards, one of the optional operating modes that while we haven't seen it adopted yet, I'm sure is not far off. So frequency watt. This is actively supporting grid frequency by changing wattage output. So we see here on the x-axis frequency. It's probably hard to read these scripts, but these subscripts, but frequency nominal, F start and F stop. Basically the delineation between the operating mode, between the standard operating range. You've also got a frequency set point on the high end and a frequency set point on the low end. So what do these ranges mean? In range 1, the grid frequency is AKA normal. The inverter is going to output at max available power, assuming no constant power factor or other curtailment by some of the other operating modes. So everything's normal, full power, full steam ahead. Scenario 2, grid frequency is high. The inverter is going to actively curtail power. This is, I think, really going to help in the scenario that we saw in the preceding slide. If the smart inverters see frequency and voltage rising, perhaps because inverters slammed back onto full power, and it sees that frequency start to rise, grid support inverters can actively curtail power to help maintain grid frequency. On the low end, so the grid frequency is low, but still within a tolerable range, the inverter is going to increase power if available. So for standard grid tie systems, you're not going to see any available power changes between 1 and 3, because that's active operation. The inverter is exporting as much power as it sees available. Where this is going to become really interesting is when we throw storage into the equation. So I'll throw out a scenario. Let's call it late afternoon. There's still available power, but maybe it's 50% of nameplate capacity. I envision scenarios where frequency watt is going to be permitted and requested, and in scenarios of low frequency or low voltage, let's say, the inverter, the utility district could call upon you to actively export power to help support voltage and frequency. We haven't seen that yet. We haven't seen the tariffs or the compensation for that yet, but I have to imagine that was part of the reason that these things were included, that storage inverters could begin to help support actively above and beyond PV production to support grid reliability. So pretty exciting stuff here. There's a couple other things that are included in Rule 21 that I haven't covered here today. I've got those in an appendix, and I can send that out if you're interested. But essentially, phase one is what we're talking about today. It's all of our requirements as set out by 1741 SA. Phase two is going to be kind of the next level of functionality, which is no. I'll just go ahead and skip to the slide. Communications. So Smart Energy Protocol 2.0 will be required. It's going to be using the SunSpec industry standards for communication. We expect that sometime in 2018. Basically, what that's going to say is, yes, we're past phase one. Everything installed has to be compliant to 1741 SA. Phase two means you need to have some communications ability required to that inverter. Phase three, no timeline, but if you think logically about what phase one and phase two means, you assume that phase three is going to happen. Interoperability. So the inverter has to be able to accept a signal in some form or fashion from the utility or regulatory agency, et cetera. I think this is going to mean that some sort of network operating system is required, either from a utility or from a demand aggregator like an Enernoc or grid services company. No timeline on this yet, but that's kind of the future that we foresee. So these are all things that will be happening in the future in California. I'm not up to speed on Hawaii, but I imagine something similar is on the books there as well. Now I'll go back a few slides. We talked through frequency watt. The obvious question I think everybody has is, what inverters are compliant? So these are all the brands that we carry here at AE Solar. Well, let me rephrase that. All of these are brands that we carry here at AE Solar. Of course, we carry many other brands that aren't necessarily on this list. Enphase, the IQ6, the IQ6 Plus, both the 60 and the 72 models are all certified to UL 1741 SA, and they're available now. The Fronius products, so the Primo 3.8, 5.0, 6, 7.6, 8.2, certified now and available now. For the larger Primo and Simo lines, the Primo 10, 11.4, 12.5, and 15.0, as well as the Simo 10.0 and 12.0. We're expecting to see certification in October, and those inverters are available now. Similarly with the Simo 15.0. And again, I want to reemphasize the point that we covered in an earlier slide. The date that you really have to be cognizant of is the date at which your permits and your interconnection agreement are approved, not necessarily when your equipment is installed. Now, I will say we're probably going to see some overzealous inspectors who say, hey, it's September 9th, you got your interconnection agreement in August, but this is the standard now. I don't know that they'll necessarily have the standing to do that and hold up your job, but as we all know, the AHJ is where the buck stops in your local area. So you will want to check with them. I'd say now, make sure that there's not going to be any surprises for jobs that were permitted and approved for interconnection before September 8th. Getting back to our lineup here, the SolarEdge A units, which we also call the classics, as well as the full HD Wave lineup are certified or available now. The three-phase units, the 9, 11.4, 10, 20, 33, certified and available now. The complete lineup of Sunny Boy products is certified and available now. It's not featured on here, mostly because I ran out of room. The SMA STP50, or the Core 1 as it's known here internally, is certified and available now, and they just received their CEC approval list this week. So that would be compliant as well. The Outback product, Radian, VFXR, and FXR models are certified now and will be available from our stock early September. The complete Solus lineup from Jinlong, and from ABB, PVI 3.0, 3.6, 3.8, 4.2, the 5, the 6, the Uno 7.6 and 8.6, and then I have here the Uno DM Plus. This is a new lineup that's going to be launched in Q1. The 3.0, the 3.6, 3.8, 4.2, and 5.0. Everything but the Uno DM Plus is available now, and of course they're all certified. So that should be your one-stop shop for making sure your product is compliant. I've got here some other resources that you may find handy. Links here to the CEC approved inverter list if you're in California, to the Hawaii approved inverter list, and I believe this is the self-supply inverter list. There's a compliance list that Calcia compiles. It's voluntary, so it's not necessarily inclusive of everything that may be on the CEC list, but could be a good resource for you. I've got here a link to the Rule 21 page from California Public Utilities Commission, where they link to the Rule 21 pages for the big three investor-owned utilities, PG&E, San Diego Gas and Electric, and SoCal Edison. You can find there on those local utility pages more specificity on what functions are going to be used and what the set points are going to be. There's a very informative, very dry webinar from UL on how the standard was developed and what it does. I've linked to that here. And there's an interesting NREL white paper on how these grid functions will actually work to support the grid that, you know, if you need something to put you to sleep at night, that's probably your go-to off of this list. In addition, of course, to listening to this webinar again. So that's the entirety of our webinar today. I've got, you know, the rest of the hour to answer any questions that may have come up. My contact information is here. Of course, you know, feel free to reach out to my team. My team of 4 application engineers are here to support you and answer any questions you have. Tech@aesolar.com is probably the best way to reach us, or you can navigate in using the 800 number. So at this point, Hannah, I think we'll open up to any questions we've got.